Welcome to this module. Like last time we have seen a few experiments related to our course, right. So, today a very interesting applications of op-amp we will be looking at. So, what happens if we have a resistive output? That means, if the sensor is changing its output or showing the output in change of resistance, what kind of electronic module you can attach with this particular sensor. So, if that is a question and that can be also a small undergrad project, right, or a MTech project where if you want to make a force sensor, or if you want to make a tactile sensor and you want to see the output, and then you have to design an electronic module to finally display these the output of the sensor onto the screen, right. Then what kind of electronic module you can design. So, to understand this concepts, first we should understand a basic or the application of the operational amplifier. So, today if you come on the screen and see what we have today experiment to understand the effect of loading and input impedance. So, what is the effect of loading and how the input impedance would help or act on the change of the output, and this is what we have studied, is not it. What we have seen is how to fabricate the piezoresistive micro cantilever. So, if you recall what we have seen here, this particular is a sensor. From here to here is a contact, here to here is a contact, you can see that red mark, right. And then this one is our resistor, this one from here it goes to all the way here, this is the resistor. So, this one is a resistor. How we can diffuse a resistor into the polysilicon, that what we have seen in the theory class. Let us quickly recall and then we will see why we have taken this example to understand the loading effect, or to understand the when there is a change in the sensor output in terms of resistance, what kind of electronic circuit we can use, alright. So, coming back to the screen, like I said, this one is your resistor, and because the material that we have used to diffuse into this silicon is boron, right, it will be p type piezoresistor, right. Why? Because the polysilicon is n type, anyway that we do not really worry about. The point is that if there is a resistor diffused into this silicon, now cantilever we all know, right. What is this cantilever? It looks like if there is a person, right. This is the example of micro cantilever, but what is the real example of cantilevers? So, if you think about a board in the swimming pool, right, there is a board, there is a person standing, he jumps into the swimming pool, right. So, what is this? This is also cantilever, it is also an example of a cantilever. Cantilever we see around in daily application. So, understand how the cantilever will work. When you press, right. So, if I press this particular cantilever, the resistance within the cantilever would change. Why? Because there is a diffuse resistor, as you can see here, there is a diffuse resistor in this particular piezoresistive cantilever. So, when I apply a pressure or apply a force, then the resistance would change, and corresponding change will tell us how much force we are applying. So, if to understand the effect of force or to measure how much force we are applying, we can use resistance as the output or resistance as a parameter, and this resistance can be used if we have a diffuse resistor, which is our piezoresistor. So, piezoresistive material, any material on which we are applying pressure and it shows correspondingly the change in the output in terms of resistance is called the piezoresistor. If we talk about piezoelectric material, if we apply pressure, right, the output would be change in voltage. So, you have seen piezoelectric crystals, right. So, these crystals are used on the basis of piezoelectric. The resistance that we are talking today is nothing but piezoresistive. That means, you apply pressure or apply force, and there will be change in resistance, alright. So, coming back to the screen. Here what was the application? The application was to understand the change in the elasticity of a material. How? So, this you see if you recall last time what we have discussed in the theory class, this is SU8 tip, right. This is the SU8 tip. This is polysilicon, this one it goes here, comes here, this is a resistor diffused, that way you cannot see, this is a cross section, this is called SEM, What is SEM? SEM is nothing but scanning, I will write it down here, SCANNING, scanning electron, ELECTRON, electron microscopy, MICROSCOPY, alright, SEM. So, SEM is a material characterization equipment used to take used for taking the images of the systems or of the devices which are extremely minute in size and difficult to difficult to get the images using the optical microscope. So, we can another advantage is we can have a cross sectional image. So, what you see here is a cantilever which is all the way edge, there is nothing here, only cantilever is there, alright. So, you can see this cross section by using the SEM. Now, what was I telling? I was on the topic of SU8. This role of this particular SU8 tip, if you see this tip SU8, is that it will help to press the material of our interest. That means that I will use this cantilever, and I have also talked in the theory class, right. I have this cantilever, I have this SU8 tip, and I take a material and I press this cantilever onto this material. Now, this SU8 tip will help to translate the amount of force back to this cantilever, alright, and this cantilever has a piezoresistor. So, depending on the deflection of this cantilever, how much it deflects, we could see the change in this resistance, alright. So, that is the role of this particular piezoresistive micro cantilever, right. Now, what we have seen? We have seen that when we apply a pressure and we apply a force onto this particular micro cantilever, there is a change in the resistance. How you will, so for example, if I say that let us use this micro cantilever to understand the elasticity of a tissue or of some material, alright, of a gelatin. So, how you will know what is the elasticity of that particular gelatin? By using the piezoresistive micro cantilever, that you have to figure it out, alright. If you see, I will also show you some of the research papers that you can go through, and you can understand how we can use this kind of devices for understanding the elasticity of the material. However, for this particular experiment, let us focus on how we can use this micro cantilever and how we can use the output of the micro cantilever with an electronic module, alright. So, the output that we can take it is using the contact. You can see here there is one contact, there is a second contact. These are called contact pads. What is called? Contact, CONTACT, contact pads, PADS, alright. So, using this contact pad, we can take the value of the resistor, or we can measure the value of the resistor, right. So, between this, if I put a multimeter and if I measure the resistance, then I will see that depending on how much force we are applying, there is change in resistance that we can measure using the contact pads, alright. Now, to measure the resistance through this contact pad, through this and this contact pad, we have to use either a process called soldering or a process called wire bonding, right. To take the contact from this pad and from this pad, either we can use soldering, SOLDER, solder, or we can use wire bonding, BONDING, wire bonding, alright, two process. Now, once we perform soldering or wire bonding, we can measure the resistance. Now, if you have this and if I apply pressure and if I see the change in resistance, right, that resistance how can I further connect or calculate or use it to convert it to some form at the output using the electronic module. So, for that it is very important for us to understand what is loading and how the loading will come into picture, and what kind of operation amplifier, or you can using the operation amplifier what kind of circuit we can formulate, alright. So, let us see the effect of loading and input impedance. That is the first topic that we have to understand. I told you about the piezoresistive microcantilever, so that you have an example of a sensor which can show the change in resistance, alright. That was a reason of talking on or repeating the piezoresistive microcantilever, which we have seen in detail in theory classes. So, resistive sensors, right, are one of the most commonly used sensors. So, when I say, or when you get this statement, you have to immediately see what are other sensors that also change the output in terms of resistance, right, because if somebody is claiming that resistive sensors are one of the most commonly used sensors, that means we have to find out that what are other sensors, right, what are the types of resistive sensors. One, I have told you, piezoresistive microcantilever is a sensor, right. Why they are most commonly used as a sensor? The reason is because they are inexpensive, they are cheap and easy to interface with ADCs, easy to use and interface with analog to digital converters. So, the output voltage or sensitivity of the most sensors are poor. Now, particularly when you talk about resistance, the change in resistance. So, if we talk about the microcantilever, the change in the resistance of the microcantilever would be extremely low, extremely small. So, if the resistance is small, that is, let us say you have a base resistance value of, for example, 100 kilo ohms, right, or we can write 1 2, or let us say 1 kilo ohm to make it easier. Let us write 1 kilo ohm, 1 kilo ohm, which is 1000 ohms, right. Let me write it clearly. Let us say we have a resistor 1 kilo ohm, which is 1000 ohms, alright. Now, if the change in the resistance is 50 ohms, change in the resistance. So, when we apply pressure or force, right, the new value, this is let us say base resistance B R, the new value B delta R or change in resistance is 950. That means the difference is only 50 ohms, only 50 ohms. This will determine the sensitivity, how sensitive it is, how much more change is there, more change from 1000 to new value, better the sensor is, alright, better the sensor. That means that if I give you a sensor which is 1 kilo ohm, and if you see that there is a change of 500 ohms, then it is really sensitive sensor and you have a broad range, to operate. In that case, your life becomes easier of how to create electronic module, but if the change is small, then it is very difficult. So, we are talking about the commonly used sensors or resistive sensors. So, if you can see on the screen again, that these sensors are inexpensive, that is good, easy to use, beautiful, interface with ADC, easy to interface, amazing. But what about the output voltage? Output voltage or sensitivity of most sensors are poor. Hence, it is required or it requires an amplification stage before interfacing with the ADCs, alright. So, that is very important that it requires an amplification stage. So, how this amplification is done, and when you do the amplification, how the loading effect will come into picture, we will see. First, let us see this one. An op amp is generally used as an amplification stage due to its electrical characteristics. Resistive elements can be made sensitive to temperature, strain and light, right. So, for example, if you have a temperature sensor, the output would be resistance. If you take about strain gauge, the output would be resistance, right. If you take about the optical sensor, again you will see lot of the thermoresistor or sensors that are used for understanding the change in the intensity, again has the output in terms of resistance, right. So, the temperature thermistor, if you say, again resistance is the output. So, using these basic elements, many complex physical phenomenon can be measured, such as fluid mass, pressure, load, humidity, temperature, etc. right. So, what is the basic elements? Just that there is a change in resistance. So, by understanding the change in resistance using different sensors, we can see that what is the or we can measure what is the fluid mass, we can understand what is temperature, we can understand what is humidity, we can understand what is strain, right, and lot of other phenomena. So, it is the sensors are heavily used, but the important point is we have, because the signal or sensitivity is poor, we have to use a amplifier, and to use amplifier we are using operation amplifier, alright. So, coming back to the screen. So, until here is okay. First is resistives are most useful, output voltage is poor, sensitivity is poor, operation amplifier used for amplification stage, resistive elements can be used for several applications. Now, let us see this particular figure. What is this figure? It is very easy, right, to understand. It is a potential divider. It is a potential divider. You are applying a voltage, there are two resistors and you are measuring the voltage across resistor R2, right. So, in the figure shown below, it is not exactly below, on side. So, you can see the figure on side, right. In a resistive is a resistive divider, if R2 right is considered as a sensor. So, let us assume that this R2 is a sensor. If this is a sensor, that means that this will change the resistance, right. So, if R2 is considered as sensor, any change in R2 resistance results in voltage change. For R2 equals to 1 kilo ohm, output is 1 volt, right. So, what is the voltage we are applying? 2 volts. What is the value of R1? 1 kilo ohm. What is the value of R2? 2 kilo ohm. What is the potential divider? R2 upon R2 plus R1 into V in. V in is 1 volt. So, if I place value 1 by 1 plus 1 into 1, is it, into 2, right, input is 2 volts, this is equals to 2. So, sorry, this is equals to 1 divided by 2, this is 0.5 into 2, which is equal to 1 volt, right, approximately 1 volt. So, this is how the potential divider works, right. We can measure the change in the or voltage across value of R2, and what we find is, we find that if I apply a voltage, it will be half of what I have applied in the input signal. So, this is the potential divider, and we all know about potential divider. So, quickly let us see why we have taken this circuit and how it is going to help us to understand the loading and input impedance. Now, so to understand here what we have seen, to amplify the circuit, a gain amplifier can be used, right. We will now look at the differential amplifier configuration and how they fare or how they can be used with each other, how they can used or interface with each other, alright. So, that means that here your output is 1 volt. If I want to magnify this output, if I want to amplify this output, I have to use a amplifier, right. So, what is that amplifier? So, let us see that amplifier. So, you understand here. So, if I want to, if a gain of amplifier of inverting amplifier. So, if a gain amplifier or a inverting amplifier has a gain of 10, right, is designed like you see here, right. So, if you see here, this is amplifier, right, and you see value of R3 and you see value of R4, then you will find that the gain is 10, So, it is designed as shown here and connected to the output of the voltage divider circuit. Ideally, it should give an output of minus 10, right, correct, because these are 10, this output of voltage divider circuit is what, 1 volt, this is 1 volt, minus 10, 10 is a gain, 10 is gain, then the output, this is inverting amplifier. So, inverting amplifier output would be minus 10, because input voltage is 1 volt, right. This is what it says, that if you use a inverting amplifier with a gain of 10, then the output would be minus 10 if it is connected to the potential divider as shown here. Easy. Now, let us go to the next section. What is that? But it results in lower output. How? This is due to loading effect caused by the input resistor R4. Now, you see here, very important, interesting. So, understand this thing. What is that? The output should be minus 10, alright, but when you measure practically you will find that the output voltage here is not minus 10, it is not minus 10. Why? Because of the resistor R4. This R4 creates a loading effect on the circuit, alright. So, we can see here that but it is lower output, this is due to loading effect caused by the input resistor R4 in the circuit shown below. Moreover, another op amp should be used to convert the phase. Why? Because you see here is 1 volt, here is minus 10 volts. So, we do not require minus 10, we require plus 10. If you require plus 10, again op amp to convert your phase back to its positive value. So, another op amp is required, that is okay. If the same circuit is connected with a non-inverting amplifier, now you see same circuit, non-inverting amplifier, right, which is figure 3, this one, with a gain of 2, right, with a gain of 2. Why? Because you have here 1 kilo ohm, you have here 1 kilo ohm, gain of non-inverting amplifier was 1 plus Rf by R1, right, which is 1 plus 1 by 1, which is equal to 2, right. So, what we are saying that if you connect the potential divider output with a non-inverting amplifier, which is here, right, what you will see? You will see it results in the output of 2 volts as expected. So, there is no phase shift, there is no phase shift. We have seen inverting amplifier 180 degree phase shift, non-inverting amplifier no phase shift, right. This is due to the fact that the input voltage is directly connected to the non-inverting amplifier, which provides a very high input impedance and an extra op amp is not required for phase conversion. So, if we talk about the inverting amplifier and we talk about non-inverting amplifier, here what we see is that we can use non-inverting amplifier to remove the loading effect. There is no phase shift, and that is why for this particular application that we have taken an example, this can be a good circuit, alright. So, this much is easy. Now, let us see the solution. So, what are the solution, alright. So, what is the solution? Using the voltage buffer along with inverting amplifier connected between a resistive divider, as you can see here, right, this is a voltage divider circuit connected to a inverting amplifier circuit using the buffer voltage follower or buffer, right. So, using a voltage follower along with the inverting amplifier connected between the resistive divider and inverting amplifier, right, as shown in figure, this figure will provide a very high input impedance, right. This is an advantage of buffer amplifier or isolation amplifier. We have seen last lecture what is a buffer amplifier, we have seen what is voltage follower. Now, we are looking at how voltage follower can be used in an electronic circuit, which is the example given here, alright. So, you can understand that use of voltage follower is to remove the loading effect on the following circuit, alright. The output voltage of the given circuit is minus 10 volts as expected. So, because it is inverting amplifier, the output would be minus 10 volts here at the output. Is it correct? Let us see, 1 volt here, it goes here, minus 10 volts, is it correct, right. So, now let us do the experiment. So, we will do the experiment to understand this concepts. We have understood what concepts, we understood the effect of loading. Let us do some experiments. So, we actually see that if I use the circuit that we have just seen, how exactly it gives you the output voltage or output waveform, on what happens when we use only voltage divider, what happens when we integrate the inverting amplifier, what happens we integrate voltage divider with non-inverting amplifier, what happens when we use voltage divider with a buffer and inverting amplifier. So, we will see this few concepts in the next slide and we will actually do the experiment, alright. So, first experiment that we have to do is to study the effect of loading and input impedance to effect this experiment, right, to study. Now, all of you know what is loading, all of you know how input impedance can be increased, right, by using what kind of amplifier, right, or a voltage follower. So, let us see this one. Figure 5, what is this? Voltage divider. Figure 6, what is this? Inverting amplifier, right. So, connect the circuit as shown in figure 5. What we will do? We will first connect the circuit as shown in figure 5, which is the voltage divider, alright. Then we will apply 2 volts DC at here input, and we will observe the output and note down the value, alright. This is the first thing that we will do. So, we will see what is the input voltage and what is V out 1. So, whatever input voltage we are giving, let us say we are applying 2 volts, what is V out 1? V out 1 is the voltage between voltage across resistance R2, alright. So, we will measure what is R2, then we will apply, then we will do the second experiment. So, let us do one by one for first experiments, and for next few experiments we will take help of Suman Chatterjee. Last time you have met him, so I will request him once again to come and help us to show the circuit on the breadboard. So, now you see the voltage divider circuit right over here, which is the first one, alright. The first one that he is holding here, these are 2 resistors, right, connected in series, and now we will apply voltage which is your input voltage, right, across this resistors, and we will measure the output voltage across resistor R2, alright. Let us see that. So, how we can apply voltage? We have to apply voltage using the DC power supply. We have to apply voltage using the DC power supply, which is in front of us. So, he is just connecting the voltage plus and ground across the resistor. Okay. So, what he has done? He has applied, if you see here closely, this red wire, alright. This comes from where? This comes from the plus 15 volts, applying plus 15 volts. Yeah, it's plus 15, right? Okay. So, this is plus 15 volts. Are we applying plus 15 volts? We have to apply 2 volts, right? Plus 15 for biasing. No. So, right now we are showing the potential divider. Okay. So, we are applying 2 volts, which is here, which you can see here, right, 2 volts. Have we applied 2 volts here in DC voltage? Can you please show 2 volts? Yeah. So, it is 2.02 volts we are applying, right, across the resistors, here, alright. So, this red wire for 2 volts is coming through here. This is the red wire, right, and it comes through your resistor here, alright, and ground, which is the another wire. This is ground which is black color wire, which I am holding, I am moving right now in to show it to you. This is the ground, alright. So, I am applying 2 volts across this resistor. What I want to measure? I want to measure what is the value of voltage across R2, So, I have this yellow color wire, right. I will connect it to the multimeter and ground to ground, alright. So, let us see. When he connects the ground and yellow wire, what we see? We see output approximately half of what we have applied at the input, 1.011 volts, right. Now, you will say that, Hardik, why we have 1 volts at the 1.011 volts at the output? It should be exactly 1 volts, right. But one thing is 2.01 volts is the input. Second thing is the resistors that we are assuming as 1 kilo ohm may not be exactly 1 kilo ohm, but it may have some tolerance. This tolerance in the resistance can cause or will cause the change in the output voltage slightly different than their expected output voltage or calculated output voltage, right. So, this is very easy. Now, what we have done? We have applied 2 volts. So, if you come back to the screen, if you apply 2 volts and what we have reached here 1.011 volts, 1.00 is okay, right. So, actually when you want to do the experiment, you have to get exact value, right. So, do not just assume that it is okay. 2.01, 1.011 volts, right, exact values. Okay. Now, we will do one more experiment. Instead of 2 volts, let us apply 4 volts. Let us apply 4 volts at the input. So, if you see on the DC power supply, now he is increasing the voltage to 4 volts. You can use fine, very good. So, this is 4 volts that he has applied across the potential divider circuit, which is 2 resistors, and he is again measuring the voltage, and what we can see, the voltage at the output is 2.007 volts, right, 2.007 volts. So, 4 volts at the input, 2.007 volts at the output. Understood? Very easy how to measure the voltage across resistors, right. So, this is a potential divider circuit. Now, we will go to the second part of part 1, that is part 1. Let us consider this as A. Now, let us consider this one, which is your second part. Now, connect the circuit as shown in figure 6. What is figure 6? If you see here on the screen, this is figure 6. This is the circuit of a inverting amplifier. You see, you are applying voltage at the inverting terminal of the operational amplifier. You have a feedback resistor, you have an input resistor, right. You have minus VCC or VEE, you have plus VCC. Here you have to measure output V out 2, all right. This is the circuit. So, we are not considered any more figure 5, we are not considering this circuit, right. We are just considering figure 6, which is this circuit, all right. So, right now do not see this one, just see this one. We have already seen this. So, let us see figure number 6. Figure number 6, what it says? Connect the circuit as shown in figure 6, connected. Now, apply 1 volt DC input directly from the power supply at V2. We have to apply here 1 volt. So, I will write here 1 volt, exactly what is the voltage we will see 1 volt, and observe and note down the output voltage V out 2. Okay. So, let me just write down 1 volt at the V2. Let us apply. So, this is the circuit, we have seen inverting amplifier, this is similar circuit. So, he is not showing you how to connect the resistors across the op amp to form inverting amplifier. We have already seen inverting amplifier. If we have the inverting amplifier, we have to apply bias voltage. So, if you see here in the DC power supply, we have already given bias voltage plus minus 15 here, plus minus 15 using the power supply to the operation amplifier. So, this is the circuit, this is the circuit, right. So, this is the inverting amplifier circuit. You can see one resistor here, which is here, and another resistor here, right. There are 2 resistors, one here, second here, all right. So, these 2 resistors you can see very clearly, these are RF and Rin. There is a operation amplifier, we have applied plus 15 minus 15. Now, we are going to apply input voltage to the inverting terminal of the inverting amplifier. Can we please apply input voltage? So, how much input voltage we are applying? We are applying 1 volt at the inverting terminal. One volt at the inverting terminal. When we apply 1 volt to the inverting terminal, What is output voltage? Output voltage is measured between 0.6 of the operation amplifier or pin, 0.66 number pin and ground, and the output voltage, is it correct? No. Yes. So, what is output voltage? You can see output voltage is minus 10.09, minus 10.09, right. So, it should be minus 10, but it is minus 10.09, that is fine. So, input voltage, and applying input voltage of 1 volts, approximately 1 volts, or to be precise 1.01 volts, output voltage is minus 10.09 volts, right. But you remember, if I make it 2 volts, if I make it 2 volts, right, do not make it right now. If I make it 2 volts, then because of the gain of 10, my output should be minus 20, is not it, but I will not get minus 20 because my supply voltage, bias voltage is 15 minus 15. We have seen this in previous experiment, so you have to remember, alright. So, I am not applying 2 volts, I am not applying 2 volts. Instead of that, just to see, we will just change, instead of 1 volts we apply half volt, which is 0.5 volt. So, can you please change it to 0.5. So, if you see in the DC power supply, if you see in the DC power supply, now we are applying 0.5 volts, yes. So, on applying 0.5 volts at the inverting input of the inverting amplifier, or the input of the inverting amplifier, what output we get? Minus 0.5 into 10 times 5, close to 5 volts we should get, minus 5, right, minus 5.13 volts. So, when applying 0.5 volts we get minus 5.13 volts, alright. So, now we know how to use inverting amplifier, how to use potential divider, right. What is the expected output? Expected output is 10.00 volts. Here expected output is minus 5.00 volts, right, because here we have assumed gain of 10, why? R3 is 1 kilo ohm, R4 is 100 ohms, R3 is 1 kilo ohm, R4 is 100 ohm, that is why gain of 10. That depends, again I am telling, this change that you see in actual values compared to what expected value is there is because of the resistance, the change in the resistance. If I say 1 kilo ohm, my resistance can be 1 kilo ohm plus minus few ohms, that plus minus few ohms would change my entire amplification factor. So, keeping in mind, if you want to have precise values of the output, then you should have precise value of the passive components that you use in the operational amplifier, got it. Okay. So, what we have seen? We have seen that if I apply voltage across potential divider, how can I measure the voltage across a resistor R2. Second is, if I apply voltage in the inverting amplifier, what is the output voltage? These two things we have seen, right. Now, let us see the another part, and that would be to if I merge both, if I connect this with this, then what will happen, alright. This is another part where I had to see that if I instead of using individually only buffer, or sorry, only potential divider and inverting amplifier, if I integrate both, that means output of my potential divider is the input of the inverting amplifier, what is the overall effect, alright. To see this, we will continue in the next module, and we will see how we can integrate both the circuits together to form the output, or we will see the effect of loading at the output in the next module, alright. So, till then, take care, I will see you in the next module.